Hello, thanks for watching my presentation. My name's Luke Demarest. Today, I'm going to be talking to you about a paper I wrote with Alex Russell and Ben Fuller called Code Offset in the Exponent. Authentication is something fundamental in our society, and more frequently, it's being mediated through computers. What this means is that instead of you verifying my identity, my phone verifies my identity. My phone then communicates with some device that you're using and says, I am who I say I am. Crucial to this is biometric authentication. What that means is we take a biometric source, such as an iris, a fingerprint, or we use facial recognition in order to identify an individual in a system. Using biometric authentication is useful over passwords because they cannot be forgotten, they are non-transferable, and they are faster than typing in an analog password. There is a downside to using biometric authentication, and that is that they are noisy. What this means is that two readings are not the same. In this work, we're going to focus on the iris biometric. These differences between readings are caused by environmental factors. It could be that you have slightly rotated your head and you'll end up with a different image for an iris. It could be that the lighting conditions are different and so your exposure is different for the iris. It could be that you're slightly farther away from the image sensor and so you have a smaller iris. All of these little differences result in different features extracted from each reading of the same iris. Another issue with using biometrics is that they don't change. This is good for authentication, but bad for security. If someone were to leak an image of your iris or your fingerprint, there's no way to get another. This means that we really want to ensure that systems that handle biometric data have no leakage. Luckily, we have fuzzy extractors, which derive stable keys from noisy sources. There are questions that we have about fuzzy extractors, such as what distributions can we prove that they support securely? How fast can we make them? And can we prove that they are reusable? What this means is that the same biometric could be used as the source for multiple fuzzy extractors. A fuzzy extractor is defined using a pair of algorithms: generate and reproduce. Generate takes in a reading from a noisy source and outputs a key and a set of public parameters. Reproduce takes in another reading from a noisy source and the public parameters and outputs a key prime. Our guarantee is that key and key prime are the same if the distance between the two readings is small. This is defined by some threshold that we set as a parameter to our system, and we call it T. Fuzzy extractors are deeply linked to error-correcting codes, which are the typical way that computer systems handle noise. There's a rich history of error-correcting codes that goes back decades that's provided good practical codes for a variety of applications. In this talk, we're going to be focusing on linear error-correcting codes. These are similar to Reed-Solomon. We call them random linear codes, where we have a generating matrix A that is chosen randomly that creates a linear error-correcting code. You'll see this as the pictorial representation, or another that I'll introduce you to in just a few slides. What's done typically in the fuzzy extractor literature is that a construction is given and a target distribution is stated, and the job of the authors is to prove that their construction supports a distribution. This acts as a link from distributions to constructions. There are many different constructions of fuzzy extractors that support many different distributions, and frequently there is a one-to-one correspondence of proofs between distributions and constructions. I'm now going to introduce the code offset construction. This is what we base our work on. In the code offset construction, you select a code word at random from a linear error-correcting code. We'll call this C. These error-correcting codes have a distance, and the unique decoding threshold is D/2. We then add this code word to our sampled biometric source. We call that reading E. We expect that C plus E is outside of the unique decoding threshold of our original code word. In fact, we expect that it's somewhere else in the code, within a unique decoding threshold of another point. What this means is that instead of trying to use the error correcting code to correct this error to get back to C, we're going to instead subtract off another reading of a correlated biometric reading. Now, if E minus E prime is within the unique decoding threshold of our original code word C, then we should be able to use the decoding procedure of the code in order to arrive back at our original code word. This is the code offset construction written out. In gen, we sample a random code word, and we add our biometric reading to it. Then in rep, we subtract off another biometric reading from that pub value, and we decode it using information set decoding, which is a decoding procedure that tries to find an error-free subset and use that to recover the original code word. So what's wrong with this construction? Well, it only supports high entropy distributions. That is, that the entropy of the distribution is at least n minus k times log q, where n is the code word length, k is the dimension of the code, and q is the size of the field in which the code resides. We hope to support distributions with less entropy than this. So the question is, what can we do to improve the code offset construction? Well, we have three observations that we can work from. The first is that information set decoding requires only linear operations. The second is that this transformation from iris to string gives us what's called confidence information, and I'll introduce that in the next slide. The third observation is that the subset selection for information set decoding happens during reproduce. That is, that the subset selection does not have to be a part of the public parameters. I'm now going to give an overview of confidence information. In iris authentication, we represent irises with bit strings. What confidence information in this setting would describe is how confident we are in the symbol that we've picked for this particular reading. I'm going to walk through a little example that I hope helps. So we have two regions, A and B, represented by a red circle and an orange circle. These two regions in this simplified model correspond to these two bits, the one with the red arrow and the one with the orange arrow on the right. In the region A, there are no other colors, so our confidence in this reading would be quite high. The region B has three different colors, and so our confidence in this particular reading might be low. We can think of this as the probability that A is described as this color with 0.89. That is a reasonably high confidence that this bit will be described this way. And we can do a similar thing for the region B. We can say the probability that this region will be described by 1 is 0.36. Now, if we have our cutoff at 0.05, that is, B is unlikely to be described by the color 1 in this region, we can say that we would describe that as a 0. The relative distance between what probability we ascribe and 0.5 is how confident we are in this description. So A would be represented by this distance, which is 0.39, and B would be represented by this distance, which is 0.14. So we would be more confident in the region A than we would be in the region B. This is what confidence information aims to do, which is to say, I think that this reading is going to match other readings of this same source. You can think of confidence information as how confident we are that a bit will not have an error. So the goal of our project today is to support more distributions, that is, distributions with lower entropy, while being able to use confidence information. As you may have gathered from the title of our talk, we're going to be discussing code offset in the exponent, which is a modification to the code offset construction. The code and the description of it remains public and in the clear. That means the generating matrix A is written outside of the group. Instead of publishing AX plus E, or C plus E, as we had talked about earlier, we publish G to the AX plus E. This is in the cryptographic group with the generator G. You can see that this code word is now in the exponent of this cryptographically hard group. And I'm going to explain why that's useful in just a moment. The intuition for why this is useful is that we can rely on the group to hide information, and by putting things in the exponent of a group, we can limit the adversary to only linear operations. This is because of the homomorphism of the group, where multiplication corresponds to addition and exponentiation corresponds to multiplication. These linear operations are all that we need for information set decoding, but limiting the adversary to linear operations only changes the dynamic and the power imbalance between us and the adversary. Here's an overview of the construction, where, once again, this code word plus our noise happens in the group. So we encode our biometric in the group, and we add it to our code word. Then we do that same subtraction, and because information set decoding doesn't require any nonlinear operations, we can still do our error correcting for our linear error correcting code in the exponent of this group. Our construction looks a little bit like this. So Gen takes in a biometric reading E. We sample a group generator R, a code A, and a code word using a variable X, where A times X is our code word C. We then compute R to the AX plus E, and output the generator, the code, and our code word in the exponent as our public parameters. Our key is R to the X, but it's actually only the hardcore bits of X. Reproduce and our decoding procedure are a little bit more involved, so we're going to go through them in a few slides, but just a quick overview here. We have another biometric reading E prime, and our public parameter is pub. We compute R to the AX plus E minus E prime. This is the same thing that we were going through graphically. Then what we do is we pick a subset, J, and compute the inverse of our generating matrix over that subset. And I'll go into some more details in just a little bit. But this gives us a value R to the S, and we compute R to the A times S. And we do distance equality checking between R to the AS and R to the AX plus E minus E prime. If there's significant agreement between these two values, we then output the key as R to the S, but once again, only the hardcore components. I will note here that in our decoding procedure and reproduce, we only do linear operations. This means that we can do this in the exponent of a group. Here's a more graphical representation of our construction. As you can see, we have the same variables, AX plus E, and we're representing them in these brackets as saying that they're encoded in the group. We use a G here instead of R, but you can just think of this as being in the group under a random generator R. So we have AX plus E, and we're representing that with Y, where Y is the noisy code word that includes the biometric E. Decoding looks something like this, where we have our value Y encoded in the group and our generating matrix A in the clear. That means it's not in brackets, it's not encoded in the group. And what we want to do is derive the information X. But what we're actually interested in, as you saw in our construction, is R to the X. And so you can think of this as trying to derive X in the exponent of the group, and so it's encoded in the group. In rep, we pick a subset J. I'm going to explain how we use confidence information in our subset selection to make this selection high confidence. In our value E prime, which we sample, we should get confidence information. This lets us know that there are some locations that have low confidence. We will want to exclude these locations from our subset J. The goal of picking a subset J is to transform our rectangular matrix A into a restricted but square matrix A sub J that we can invert. By picking locations to exclude in E prime, we'll also be excluding them in Y. This corresponds to excluding rows of our matrix A. So Our subset selection of high confidence locations gives us a subset that we can restrict our generating matrix to. We call this J. We end up with a square matrix, which we then can invert. We multiply this square matrix by our restricted noisy code word minus this other biometric value. If this is indeed an error-free subset, then this multiplication should give us x in the exponent of the group. For security of our scheme, we give an indistinguishability game. The adversary is tasked with distinguishing a noisy code word in the exponent of a group from a uniform value in the exponent of a group, given the generator of the group and the code A. In the pink here, the pink case, we have that the adversary actually receives the noisy code word. In the teal case, the adversary receives the code, the generator, and uniform values in the exponent. If the adversary cannot distinguish between these two settings, then the adversary cannot be learning anything about the code word. Our hope is that for broad distributions of E, that the adversary does not have any non-negligible advantage in distinguishing these two cases in this game. For our security game, we show that a characterization of distributions called maximum inner product unpredictable over random subspaces suffices to prove security for this game. So, rather than proving that our construction supports a specific distribution, we are going to prove that a construction supports a characterization of distributions. This means that instead of having to prove that a new distribution is secure using our construction, if you instead prove that this distribution meets the characterization of MIPURS, then it will automatically have a secure construction. This adds an extra step, but increases the ease of proving security for fuzzy extractors for distributions that match our characterization. MIPURS has a complex definition, so I'd like to provide some intuition. The adversary is given a description of a biometric distribution. This is not the sample that we take, E, but instead the distribution from which E is sampled from. The adversary is also given a linear error-correcting code, shown here as a code word with a unique decoding threshold, but think about this as a generating matrix A. What we want to be true is that no polynomial adversary can generate a BG pair such that B, taken as an inner product with E, is G. Once again, B is in the null space of the code A, which the adversary has a description of, and B, when taken as an inner product with E, produces G, where B and G are adversarially chosen. Now we're going to discuss what's included in MIPURS and its relationship to the existing literature. So, prior work has shown that all subsets have entropy implies that average subsets have entropy, which implies fuzzy min entropy. Introducing MIPURS, we show that MIPURS implies that average subsets have entropy. We also show that MIPURS and all subsets have entropy are incomparable, and I'll describe that in a little bit. We then provide three different types of distributions that all satisfy MIPURS. I'm going to talk a little bit about what location and independent sources are. I'm going to walk us through more about the general entropy case, and I'll also talk about this relationship with all subsets have entropy. Independent sources are sources where each symbol contributes constant entropy. This means that the error in each location is independent from each other location. Location sources are sources where locations are chosen and the errors in those locations are uniform in the group. This means you can think of it as an inner product between a binary location string and a uniform vector, where the binary location string is 1 in positions where there is error, and therefore those positions will be uniform in the group. This is like a one-time pad, but only in specific locations. I'm now going to talk about MIPURS and all subsets have entropy. There are two simple examples that I'd like to walk through to show that these two characterizations do not contain each other. In the first distribution, we're going to fix the first k locations of the distribution, and the rest are going to be uniform. In the second distribution, it's going to be drawn from a Reed-Solomon code with a specific dimension, that is n minus k minus 1. What we show is that if you fix the first k locations, this is actually still a MIPURS distribution, but clearly this first subset does not have entropy. In the Reed-Solomon case, these two dimensions line up, or these two codes line up, the error correcting code that we use and the Reed-Solomon code line up so that their null space is guaranteed to overlap. This means that it is not a MIPURS distribution, but you can still show that all subsets do have entropy. This means that MIPURS and all subsets have entropy each contain a distribution that is not contained in the other. I'm now going to talk about the general entropy requirements for MIPURS. If a distribution has minimum entropy greater than log q to the n minus k, we can show that it's MIPURS using 3 steps. 1, we bound the size of an orthogonal set. This is not a linear space, but instead a set that it predicts inner product 0 with reasonable probability. We then show that predicting any value, not just 0, isn't much easier than predicting 0. And then we show that vectors with this entropy don't lie in this set with high probability. This is just an overview for what we have for our general entropy requirements. It is a significant amount of our paper, so I would encourage you to go and read the details there. I'm now going to recap what we've discussed about MIPURS. It's a characterization that sits between distributions and constructions, hopefully making proofs of fuzzy extractors a little bit easier. We've shown how it interacts with existing literature on fuzzy extractor distributions, and we've given some intuition for what it means and how we define it. I'd like to wrap up by revisiting our contributions. We have a code offset in the exponent construction, which allows us to use confidence information. This allows us to speed up our decoding procedure considerably by picking high confidence subsets. We also are able to prove security for this construction using lower entropy distributions than other fuzzy extractor constructions that use confidence information. That means that we have a fast and secure fuzzy extractor that is able to use the information that we get from biometrics. Thank you, and please, if you have any questions, feel free to reach out. My name's Luke Demarest. Have a great day.